Hi, everyone. Okay, so last time we performed the separation of variables in the Schrodinger's equation, hoping to seek a modal solution, also known as normal modes. These are very special solutions. In general, the wave function does not separate into a product of time part and a spatial part. But we're looking for such solutions. And the reason is that, well, if we have such solutions, we can build any solution, kind of like a Fourier series. So modal solutions or normal modes are very, very important. When we performed the separation of variables, we found that the time part has a general solution, e to the minus e over h bar times t, times maybe a constant. That's it. But the spatial part satisfies something called time-independent Schrodinger's equation. So last time, we stop right here. We separated so notice this is an uppercase psi, this is a lowercase psi. We use lowercase psi for the spatial part, right? So this is seeking a variable separable solution. And these are modes. We saw that with string, they might have shapes like this. In general, modes will have different shapes, not necessarily sine waves. Modes are not always sine waves. No, 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 no. Only in very simple situations they are. So we saw that psi satisfies something that's called time independent Schrodinger's equation, or I'm just going to call it TISE in the future. And it's this. Remember E, this is a separation constant. And to remind you what that means is when we do the separation of variables, then we're able to manipulate terms that everything is a function of time on the left-hand side, everything is a function of space on the right-hand side. And the only way that function of space can be equal to function of time is if both are equal to a constant, like 17. And that constant is called a separation constant. We called it E. And the reason we called it E is because later we will see that it has the meaning of energy. So that's the time-independent Schrodinger's equation. Of course, we also need boundary conditions. We can't solve a differential equation without boundary conditions or initial conditions. Basically, you need some data about what happens to psi on the boundaries. So you see that we cannot proceed further in general. And the solution will now depend on the U. Now, what is U? U is a potential energy, and potential energy encodes what the particle that we're describing by the wave function is interacting with. So you can have different physical situations, and those different physical situations mathematically manifest themselves as different U's. So if you have an electron interacting with a proton, it will have one U. If you have an electron in some kind of a uniform electric field, like between parallel plate capacitors, it would have another U. It would have, if you have electron interacting with some kind of a charged solid, some kind of a cloud of smeared charge, it will have yet another type of U. If you have an atom interacting with other atoms, it will have yet another type of U. And if you have an atom interacting with another atom, it will have yet another type of U. So each different physical situations, each different physical scenario corresponds to a different u. I hope you understand it, but I'm going to write that down. This is why potential energy is so important. Well, what kind of physical situations do you know? Well, we know that we've already seen that quantum behavior, the wave behavior of particles, it sort of pops for small things. It's true that quantum mechanics does not have to be restricted to small entities, but in practice, it becomes most noticeable for in the micro world. Well, what's a quintessential microscopic system? Well, it's atoms, right? So an atom, you have, well, so here's a simplest atom, hydrogen atom. You have a proton and an electron, right? So this is proton and this is an electron. So this is H atom, just a simple atom. And let's say I'm going to keep the proton fixed in place. Yes, in practice, it doesn't have to be fixed in place, but if we can solve a problem where the proton is fixed in place and electron is allowed to move, we can solve the problem in which the proton is not fixed in place. There's a procedure for that. So here's the x-axis, and I can plot the potential energy of this particular scenario versus the x-axis. And you know that the potential energy here would be K Q1, Q2 over R. So if Q1 is positive and Q2 is negative, the whole thing would be negative. And so that potential energy looks like, it looks like this. And the same thing on this side. So I'm drawing this in 1D. And looking at this potential energy graph, you can tell right away that if energy is going to be below zero, in classical mechanics, you're going to get a bound motion. Classically, we can talk about motion. Quantum mechanically, we cannot, but classically, we talk about motion. So classically, you have a bound motion or bound state in quantum mechanics. State means wave function. So the property of the wave function is drastically different between when E is less than zero versus when E is bigger than zero, just as the classical motion is drastically different between when E is less than zero versus E is bigger than zero. Okay, and so here you have E, oops, sorry, what I meant to say is here you have E is bigger than zero, and so you have scattering in classical or scattering state wave function in quantum mechanics. And this is E is less than zero. So in 1D, bound motion would involve a particle shuttling back and forth between the two turning points. If E is less than zero, E is bigger than zero, it speeds up and then slows down, but never stops. 1D is a very pathological situation. Usually this problem is not analyzed in 1D. It's a lot more relevant in 2D. Now in 2D, we plot potential energy versus the radius, and radius is always a positive quantity. So in 2D, we do this. So this is 1D. This is the x-axis. So in 2D, you have the following situation. So you have a proton, and then you have an electron somewhere. And what kind of motion can happen in 2D? So the 2D classical bound motion can be either ellipse or a circle, and 2D classical scattering motion is either hyperbola or parabola. So the way it works is that you have an electron coming from very far away, and it gets attracted and deflected, but it's not captured. It doesn't end up revolving around the proton. So this is an electron. So this is hyperbola. Or you can also have a parabolic trajectory. But it's very rare. You have to choose initial conditions very, very carefully. So a quantum version of this problem would say, well, let's take this potential energy function in 2D or in 1D and solve the Schrodinger's equation with some appropriate boundary conditions. And instead of obtaining a trajectory, which even classically is not a trivial thing to do, instead of obtaining the trajectory, you would obtain the wave function. And for that wave function, from that wave function, you can extract statistical information about position measurement outcomes, momentum measurement outcomes, and so on. So that's the program. That's how it will work in quantum mechanics. Classical mechanics will calculate trajectories. In quantum mechanics, we calculate wave functions. That's really what we're doing. Basically, this potential energy is devoted entirely to chapter 7. If we get to it, great. If not, then you will see it at some point in the future. What other kinds of potential energies do you know? Other simple potential energy functions. Well, you know parabola, right? So you know spring potential energy, right? So U equals 1/2 kx squared, spring potential energy. It corresponds to a mass on a spring. So here's its equilibrium position. It's oscillating back and forth. Now, when you look at this, you might say, well, I believe you that this is relevant. This is relevant for atoms. You can predict behavior of atoms. You can understand atomic spectra, atomic transitions. It all comes from solving the Schrodinger's equation, finding the wave functions, finding the energy values. I forgot to mention that you don't only find wave functions, you also find energy values. You might say, I believe you, but why do I care about this? Like, when would I attach an electron onto a spring? And so I want to impress upon you that if you can solve this problem, you can very easily solve this problem. You might say, okay, fine. Well, when do I have two particles on a spring? Springs don't exist in microscopic world. This is all just for textbooks. It's all just for making us work. I don't believe that this is a relevant problem. What if you have two atoms, right? So you have, O2 molecule. So here's an oxygen molecule. And so you have an oxygen atom and an oxygen atom. And they interact. it's in a stable configuration. So the two oxygen atoms are not too far, not too close. And in general, they will vibrate. How do they vibrate? What kind of forces do they experience? You see, spring, it's just a model for a linear restoring force. So when you hear spring, what you really should hear is not like a piece of metal coil that you buy in Home Depot. By the way, springs are not easy to find in Home Depot, but the point is that spring is not really a literal spring. What it really is it's a linear restoring force. And let's say if I pin this atom in place and I plot the potential energy of the two atom system. So this is atom one, and this is the, let's say this is the, yeah, it's okay. I can make it the radial coordinate. I can make it the x coordinate. In principle, the other atom can be on the left-hand side. Let's say the other atom is always on one side, right? So let's think of this as a radius. Think of this as a radial separation, right? So this is a radius. Well, if you squish the two atoms together, if you bring the two atoms really close, that takes a lot of work. Remember, when you do some work on a system, you increase its potential energy. For example, if I apply an external force to the two masses on a spring, on one mass on a spring attached to a wall, the work that I do, the energy that I expend from having breakfast, it gets stored in the potential energy of the system. So the potential energy increases very rapidly. And in general, the potential energy landscape would look something like this. How do you relate forces to potential energy? So what I want you to, where I want you to be is I want you to be very comfortable at reading potential energy graphs, very, very comfortable. So when you look at a potential energy graph like this, you say, aha, force equals minus derivative of potential energy. So that means this has a huge restoring force. The force on this second atom is enormous. It pushes the atom. It does not like the two atoms to be close together. No. And when the second atom is too far, it also says, no, 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 come here, come here, come here. I want you to be here. So there is a restoring force here. And so you would say that the molecule is stuck in a potential energy well when the energy is less than zero. So, right, you see, so this E is less than zero. The motion of the second atom, if we hold the first atom in place, would be a bound motion. And what would that atom do? What would the second atom do? It will oscillate. Oscillate between what? Oscillate between the two turning points. You see, reading potential energy graphs, very important. So that's the classical motion. I want to make sure that we talk about classical and we talk about quantum. Talk about classical and we talk about quantum. So classically, the second atom would oscillate. And while this is not a parabolic potential energy function, but close to the equilibrium, it's approximately parabolic. And parabolas occur almost universally around equilibrium points. It's very hard to find a potential energy that has an equilibrium that cannot be approximated by a parabola near an equilibrium. You can build such a potential energy, you can find such, but this is a generic situation. So generically, when the displacement between the, when you displace the molecule away from the equilibrium length by a little bit, it will oscillate exactly as two masses on a spring would. And that's why solving a problem of a harmonic oscillator is a big deal in quantum mechanics, because by solving this problem, you can predict vibrational behavior of lots of things, molecules, whatnot. So this is called a harmonic oscillator, or so the quantum version of this is called a quantum harmonic oscillator. The classical version of this is classical harmonic oscillator, and it can be modeled as a mass, as two masses on a spring, or even one mass on a spring. If you can solve one mass on a spring, it's easy to go to two masses on a spring. So this is harmonic oscillator. The blue is harmonic oscillator. And I will tell you the solution of the harmonic oscillator. I will tell you the solution to the time-independent Schrödinger's equation for the parabolic U. In other words, I will give you a set of wave functions and a set of energies that correspond to the harmonic oscillator potential energy function. But even that is pretty hard. I will state the solution, but how to solve it, you need to take a more advanced quantum mechanics class. It involves lots of math, actually. So given that this is a generic situation for bound states, generically, bound states have some kind of a well. So you see, generically, bound states exhibit a well-like potential energy function. Like a well. I forgot to mention that if E is bigger than 0, that corresponds to scattering motion classically, where the atom either comes in, rebounds, and goes back, or just gets ripped out. And quantum mechanically, there's also an analog for that. It's called the scattering state. But back to my point is that generically, you will have some kind of a well. So here is a well that corresponds to a molecule. It can be approximated by a parabola. Here's an interesting kind of a well with a singularity inside that corresponds to an atom. It's kind of a well. It just has an infinity inside, but it's a well. And so wells are a very generic situation. And so we can do models, right? So we can take a well-like potential energy and we can try to construct a model. So we can try to construct the following model. It's rather artificial. It is rather artificial. It would be doubtful that this occurs in nature, but it is simpler to solve. Why is this simpler to solve? Tell me. Why is this piecewise square thing easier to solve? Because there is no force at these points here, in these regions, no forces here. And we already know how to solve the problem without force. We already looked at the free particle Schrödinger's equation. We already know what its solution is like. It's a plane wave. And so the solution here will be plane wave here, plane wave here, plane wave here. And we just have to stitch those plane waves between these three regions. Okay. How could you build such a thing in the lab? Well, what this says is that you have three regions without force, and you have one region with a positive force, negative slope, positive force, and one region with a negative force. And you can do that by placing parallel plate capacitors. Your textbook has a beautiful example. I'm going to steal their example. I really like this. And you can put a positive particle here, proton. And what you can do is you can charge this positive, negative, negative, positive. And you see what happens when the proton enters the region between the plates. There is an electric field that does something like that. And that electric field will apply a stopping force and will stop. So describe to me the motion. Right? So potential energy graphs, you should know how to read them. The proton is moving with a, let me see if I can try to find a way to point. So out here, the proton is moving with a constant speed. Then it would accelerate here, it would move faster, and then it would decelerate, and then it would move with a constant speed. So that's the scattering motion. What if the energy is given by this value? Well, we know that proton cannot be found outside these two turning points. So describe the motion for me now. Read the potential energy graph for me. Describe the motion from looking at this potential energy graph. Well, in between, in this flat region right here, the proton moves with a constant speed. It has no force. When it enters the region between the plates, it's experiencing a negative force, positive slope, negative force, and it decelerates. It's losing kinetic energy until it lost all kinetic energy, and it will stop somewhere in between the plates. At that point, it has a force. That force immediately accelerates it back. It picks up the speed, then it coasts along with a constant speed that it enters the region between these two plates. It slows down, boom, it loses kinetic energy. You see? So that's what's going on here. I'm slightly cheating here. Let me try to thicken this up a little bit. Folks, I want you to focus a lot on reading, on learning to read potential energy graphs. It's a very important skill. Yes, the best you can get from that is predicting classical motion. And we're here to do quantum mechanics. But in order to reason about quantum behavior that you don't have intuition for yet, you have to at least have a good sense of what a classical particle would do. So if I plot the force, I can try to plot the force versus x. And so within this region, I have a negative force. Then I have here I have a positive force. You have a zero force, and I have a zero force, and I have a zero force. You see that's the force. So this is the force, and this is the coordinate. So here's the potential energy, and here's the force. Do you see how everything fits together? So my point is, you actually can build physical scenarios that are precisely described by this potential energy graph. And my claim is that it should be easier to solve the time-independent Schrodinger's equation for this potential energy graph. Even this is hard to do. This is not easy to do. Right now, you would not be able to do. You need to have some skill. So we can simplify further. So you see, we started with some kind of a generic well. Then we looked at a model well that's piecewise linear. The fact that it's constants in a bunch of regions is what makes it simpler, but it is still hard to do. Simplify further. What if I bring the plates so close together that I don't worry about resolving the motion of the proton inside in between inside the capacitors? I don't care about what's going on inside the capacitors. So I can construct a potential energy landscape that looks like this. It's basically 0, and then it's negative, and then it's 0 again. Okay, so basically this is bring the capacitor plates really close, i.e. don't resolve the behavior of a particle inside capacitors. Okay, so here's a potential energy graph for you. Read it for me. Let's say I have energy that facilitates bound motion. Describe to me, describe the physical situation. Read it for me. Read the potential energy graph for me. Describe what the particle would do. Well, in between the these 2 points, in between the so let's say x plus and x minus, it coasts along with a constant speed, and then it just stops and turns back. We're not resolving the slowing down that takes place inside the plates. It happens over a very short distance. So notice if you charge, you see if you have a, if you realize this with a capacitor, that means you apply a voltage difference between the plates. Potential energy is then given by Q times V. The voltage, so if I have a certain step in potential energy, that means I have a certain step in voltage. I'm not changing the voltage, I'm bringing the plates together. If you keep the voltage between the 2 plates the same and you bring the plates together, the electric field goes up because the electric field goes like delta V over delta X. The electric field goes up means the force goes up. Does it make sense that as you bring the capacitor plates together, the force goes up? Well, yeah, because the slope right here increases and the slope is the force. So what happens is, in terms of this model, the particle experiences an infinite force over an infinitesimal distance. It basically coasts along, ping, it stops, coasts along, ping, it stops. So the particle will shuttle back and forth between x minus and x plus. It will experience an infinite stopping force, but over infinitesimal distance. Yet the potential energy difference is still finite. That's what we're doing. That's what happens when you bring the plates close together. And the particle will shuttle between x plus and x minus like a bead in a pinball machine, like ping, 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 ping. That's what this graph is telling us. So compare a realistic well where it goes to a less realistic well. Something like that. I'm not gesturing properly because, well, it's accelerate, coast along, decelerate, accelerate, coast along, decelerate. Still somewhat smooth. And even less realistic, but the essence is still there. In all of these problems, the particle is shuttling back and forth. You see, so we're simplifying, 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 but the essence of the problem is still there. In all 3 versions of the problem, from a realistic well to a less and less realistic well, they all describe a particle being trapped between 2 turning points. You see, physics is the art of squinting your eye at the world and finding the simplest way to describe its complexity. It's an art because you have to know how to dispense of non-essential details and keep the most essential details so you capture the essence of the problem. The essence is still here. You still have a particle trapped in between 2 points. So this is called a finite well. This is called a finite well problem. And we will do that on Wednesday and Thursday. It is still pretty mathy. You will not like it. It's a very mathy problem. Yes, you have plane waves in the first region, you have plane waves in the third region, you have a combination of plane waves in the middle region, which will translate to sines and cosines, but we have to stitch them together somehow. And that stitching is what's going to give you cringe. Okay, you're not going to like this. This is a very heavy math. Even this, it's still rather difficult to do. So we simplify it even further. Notice that in this problem, if the particle has enough kinetic energy, it will be able to overcome that infinite force that's acting over infinitesimal distance, and it will be able to escape the capacitor plates, just like here. If I give the particle enough kinetic energy, yes, it moves fast here, fast in between the plates. It slows down within the capacitor. Sorry, it moves fast in between the capacitors, then it slows down within the capacitor, but it will have some kinetic energy left and it will escape. So I'm going to simplify it one more round. I'm going to make the potential energy infinitely high. And I'm going to change the problem a little bit. I'm going to place the bottom here. Remember, we can always translate the potential energy by any arbitrary constant. So this is x minus, this is x plus. And basically, this is a very artificial problem. Equals 0 for x less than x plus bigger than x minus. I'm gonna tweak it one more time, but I want to show you a progression of simplification. And infinite outside. Infinite means particle cannot be here, quantum or classical. Quantum classically, it means the particle cannot be there. Quantum mechanically, it means you will never find the particle outside. It means its wave function will be 0 outside. And that's where the simplification comes from, because then we only really need to solve the Schrodinger, the time-independent Schrodinger's equation within this well. The particle is also oscillating back and forth like a bead in a pinball machine, ping, 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 but it will never escape no matter what its energy is. The reason that this is simpler is because, well, quantum mechanically, this is simpler than this. So this is called an infinite well. The reason that infinite well is simpler than the finite well quantum mechanically, although classically they're equally simple or equally difficult, is that the wave function is 0 outside. It makes problems simpler. And you will see that when we do solve the Schrodinger's equation for this problem, it will actually be very similar to a wave on a string. So this is a set of simplifications. I hope I guided your mind, guided your thought process. I hope you see what we're doing. We're starting with the time-independent Schrodinger's equation. We said we cannot proceed until I specify the u. Well, what kind of u's could we be interested in? Well, we're interested in simple potential energies that correspond to some kind of realistic bound situations, like an atom. Okay, that's chapter 7. Well, here's something else, harmonic oscillator. When is harmonic oscillator relevant? It's relevant for many things near equilibrium. And so here's a generic well. Generic well has some kind of a minimum, hard to solve, so we resort to models. Well, how about this model? Okay, we can actually build it in the lab. Hard. Simplify further. Still not too trivial. Simplify even further. And we're going to work on that for the next 2 days. So today and tomorrow, we will solve the infinite well problem. It's also called particle in the box. Particle in the box. When I was a student, we called it particle in the box because the particle is stuck inside a region of space. It cannot escape. It's in the box. If this was a 3D, this really would be like a box. Particle just cannot escape. So we're going to stop here. In the next short video, I'm going to set up the problem. And in the third video, I'm going to solve the time-independent Schrödinger's equation for this scenario. Before I do this, I want to tell you it might seem like we stripped so many details that this is too artificial. Here's why we're doing this. It turns out that this problem will have certain features, and those features are found in more realistic problem, and even in more realistic problem, and even in more realistic problem. So this is a great model. A lot of features of the solution, the way that wave functions behave, the set of wave functions that we obtain, the set of energies, a lot of that will carry over qualitatively to more realistic problems, which are hard to solve. But if you learn to understand the solution to this problem, you will be able to intuit about quantum solutions to more complicated problems. Even if you cannot solve them, you will be able to reason out what those solutions do. And this is why we spend time on finite well, on infinite well, and a little bit on finite well. Okay, so this is part one, models, wells, and in the next short part, I will set up this problem. I will set it up, and then we will actually solve it. Okay, all right, thanks.